Hi folks, welcome back and thank you for watching this lecture. In this lecture, we're interested in complex plane and working with complex numbers. Now, we have worked with complex numbers in a different context, if you will, as an algebraic construct. And what I'm interested in this lecture is the connection between trigonometry and complex numbers. So I'm interested in, if you will, the polar form of complex numbers. Now what I have here is what we call the complex plane, or is also known as the Argand plane. Let me put the word for you, the Argand plane. Now in typical Cartesian coordinate, the horizontal axis is the x-axis, the vertical axis is the y-axis, correct? But when we talk about the complex plane, the horizontal axis is often labeled as the real, or simply RE, the real axis. And the complex axis, some books label it as I, or others just go IMAG as an imaginary axis. Now this whole idea of complex numbers is very fascinating, and typically electrical and electronics engineers use complex numbers in the study of AC alternate currents, AC circuits, and also in the field of subatomic physics, such as quantum physics and physics of particles that are smaller than atoms. I mean, we're getting into quarks, fermions, bosons, and so on and so forth, is where complex numbers have the biggest usages. But other area of science use it sometimes to have a simplified version of another expression. So, but at any rate, no matter who uses it, we're interested again in trying to look at or explore the relationship between the algebraic form of complex numbers and their trig form or polar form. Okay, now if you recall, in algebra we use x plus yi as the general form of a complex number, where we called I to be square root of -1, so that I squared is -1. Correct, and we did quite a bit of work earlier with this complex numbers, such as adding, subtracting, multiplying, and dividing them. Okay, now in this work, let's say here's the complex number, call it z. The horizontal component, the real part of it, if you will, is x, and the imaginary part of it is the y. Okay, and again, we're looking at what we call the Cartesian form, right? The Cartesian form of the complex numbers. Now, the distance from the origin to z, namely this distance, is called the modulus, or absolute value of the complex number. And there you go. And I'll explain why it's called absolute value in a moment. So z is simply the square root, because it's the distance from 0 to z. We can use Pythagorean to establish that relationship, right? X squared plus y squared, square root of that is called the modulus or magnitude. Let me write that. That's the modulus slash magnitude of the complex number. All right. Now, the absolute value. Why is it called absolute value? Well, I'm going to say if y is equal to 0, in other words, if the imaginary part of the complex number is 0, then square root of x squared plus y squared reduces to simply square root of x squared, right? And we know from algebra that square root of x squared is absolute value of x, because the mere presence of square root simple means we're looking at the principal value. Now, because this is absolute value of x, and at that point, the complex number has reduced to just x, right? What was z is now really x. So you replace x with z, and that is why it's called absolute value of complex number. Alrighty. Now, every complex number we can also write as conjugate. The conjugate of a complex number, we need it because later on we're going to work with conjugates. So what is a conjugate of a complex number? Z, we're going to go Z with a bar on top, and it's going to be x minus yi. Notice the difference between the original and the conjugates is the change of sign. So these two become conjugates of each other, of one another. Okay, so conjugate of x plus yi is x minus yi and vice versa. Now, something interesting, a property of complex number and its conjugate. The product of every complex number, x plus yi, and its conjugate, x minus yi, is going to be real. And here, if you do FOIL, you see that the OI in FOIL will give you opposites. So you simply square the first term, and then minus, you square the second term. And we know I squared is -1, and hence we get x squared plus y squared, which is real, right? It's going to be at least 0. And this is going to be absolute value of z quantity squared, right? So we can say that another way to think of it is that the magnitude of a complex number is simply square root of z times z prime. I'm not z prime, but z bar, sorry. Okay, so this is pretty much the basic of, again, we've done complex numbers in the algebra portion of the course, so we're not going to add, subtract, multiply, and divide it. And also I want to recall that if the real part of the complex number x is 0, then the complex number becomes what we call pure imaginary. All right, now let's take a look at the polar form of the complex number. Now, to interject the polar form into the work that we are doing, let's do the following. Suppose now I'm going to, this distance from 0 to z, we're going to call that r, okay? And the angular rotation here, the angle that's formed from the real part to the complex number, we're going to call that angle theta. Okay, now in polar form, so you can kind of imagine now, throw the polar axis overlay on top of the Cartesian, the Argand plane, and we can see now the connection between complex numbers in polar form to Cartesian form. So let's go with the polar form here, since we are talking about polar coordinates, so that's our focus here. The polar form. Now, if you recall, going back to polar form, we established this relationship between rectangular and polar coordinates of a point. X is r cosine theta, and we said y is r sine theta. Right? We established this earlier. Now, if r is greater than or equal to 0, and the argument of complex number theta is what theta is, the argument of complex number is between 0 and 2 pi. Again, let me emphasize, this is what we call the argument of z, the complex number. Then it is possible to write the complex number in polar form. Here's the x plus y I. You see that? Now, sometimes this is written as in shorthand as r, and then cis, using r cis notation. R cis theta. C is for cosine. Okay, I is the imaginary, S for sine. So we write it as r cis theta. Okay, that's a very common way to write it as well. But remember, we're talking about the Argand plane. That means you have real and imaginary axes here. And as before, the modulus of that complex number is square root of x squared plus y squared, and that is now r. Notice r is the same thing as the modulus here of the complex number. Next, let's talk about Eulers' formula. Very fascinating, Euler's formula. Euler's formula is actually very interesting because it connects 5 of the most important numbers in all of mathematics, brings them all together. Now here's what Euler formula reads. If theta is any real number, then e to the I theta can be written as cosine theta plus I sine theta. Okay, so this is what Euler's formula is. Now the proof of this, by the way, usually in the second semester calculus, we prove this using infinite series. Now I mentioned that Euler formula actually is interesting because it brings the 5 most important numbers in all of mathematics together. And here's actually an example of Euler's formula. If you look at e to the I pi here, so I'm just going to try this Euler formula where theta is pi. So what is this going to read? Well, it's going to say cosine pi plus I sine pi, correct? And we know that sine of pi is 0. So this becomes in turn just cosine pi, which is -1. True? Now check this out. And remember, e is irrational. It's about 2.718 ... Pi is irrational, 3.14 ... And I is not even real, right? But here's what's fascinating. You have an irrational number e to the power of irrational number pi times an imaginary unit I, e to the I pi, equals the real number -1. Now if you move -1 to the left side, and this is the 5 numbers I was telling you about. Isn't that beautiful? That is so cool. E to the I pi plus 1 is equal to 0. The 5 numbers, e, I, pi, 1, and 0. That's the relationship between these 5 numbers. So hopefully you also get excited about this as much as I do. Alrighty. Now, going back to the Euler's form. So we said that z is equal to r, and we mentioned this. The Euler form was this one. That was the Euler formula. Okay. Now, complex number was r cis theta. Correct? We can write the complex number right in here. Z is equal to r cis theta. Well, that cis theta, we can actually write it as r cosine theta plus I sine theta. And if you look at the Euler form, that's just the Euler's portion, Euler formula. We can write it as r times e to the I theta. And this is commonly known as the exponential form. Exponential forms come in very handy with complex numbers when we multiply, divide, do things like or raise to a power. Here's the exponential form of the complex numbers. Okay, now having talked about the exponential form, check this out. Let's say we want to multiply. Let's say we want to do product and quotient of 2 complex numbers. So on the product side, let's say first I need to define a couple of complex numbers. I'm going to go z1 be r1, e to the I theta 1. I'm going to let z2 be r2, e to the I theta 2. So I have 2 possibly distinct, meaning different, unique complex numbers. They could be the same also, but in general, that's not the assumption. So how do I multiply them? Well, I'm going to multiply the first complex number times the second complex number, right? And there you go. Now when we multiply these, r's are real, right? So r1, r2, that's just the product, r1, r2. And using properties of exponents, e to the I theta 1 times e to the I theta 2 becomes e to the I theta 1 plus I theta 2 using properties, multiplication property of exponents, which in the numerator, if you factor I, get I theta 1 plus theta 2. Okay, Therefore, if you go back now to the cis notation, I can write this as R1, R2, and this would be cosine of theta 1 plus theta 2. That's the argument in the exponential form of cosine, plus I sine theta 1 plus theta 2. And there you go. So this is the, in a way, we proved how to multiply two complex numbers, and this is the proof. If you don't use the exponential form, you can just go from the Eulers form, multiply them, and then you can use the law of, and you can use the sum formula for cosine to arrive at the same conclusion. But this is a lot easier. Let's look at the quotient or division of two complex numbers. So I'm going to divide r sub 1 e to the I theta sub 1 divided by the second complex number I theta 2. And for this one, again, the r's are real, so I'm going to divide those. Using the quotient rule of exponents, I can write it as such. Now in numerator, I can factor the I, and this time it will be theta 1 minus theta 2. And there you have it. And again, in using Euler's formula, you can also write this as r cis theta 1 minus theta 2. Oh, not the product, sorry, I'm doing the quotient. So it's r1 over r2 times cis. The product using cis notation is r1, r2 cis theta 1 plus theta 2. Okay, so we can quickly and easily multiply these complex numbers. If we have the exponential form, it's going to go really easily. Now, this is an interesting theorem. Let me state this theorem for you. There is a theorem here that says that the argument of complex number is periodic. Let me write that in words, actually, what I just said. I just said that the argument of a complex number is periodic. Now, what do we mean by this? The argument of a complex number, or that's in r times e to I theta. Remember, that's the complex number z. Okay, what is the argument? The argument is theta. Okay, the argument of a complex number is periodic. So let's see what this means. So this r times e to the I theta, I can write it as r times, using Euler's formula, right? Cosine theta plus I sine theta. Well, that's just straight exponential form to trig form. And by the way, this is what the trig form is. Okay, the trig form involves cosine and sine. The exponential form involves base e. Okay, now we know that sine and cosine are periodic, right? Because both of those are periodic, that means I can write cosine of theta as cosine of theta plus 2k pi, couldn't I? Remember, k is an integer in this work. And likewise, I sine change theta to theta plus 2k pi. Right? That's because, you know this, but let me just write it. Because, for example, cosine theta is the same as cosine theta plus 2k pi. That was the definition of a periodic function, right? If it can be written in this form. So both sine, cosine, all three functions are periodic. So there you go. Now, if I look at the argument in here, the argument of this complex number is now theta plus 2k pi. So I can write it as e to the I times the argument, which is theta plus 2k pi. And there you go. That's what this theorem means symbolically. So in words, again, we say that the argument of complex number is periodic. Alrighty. So that's all pretty much like it would be the lecture part. Now let's take a look at just a few examples here. We're not going to do a whole heck of a lot with complex numbers in this pre-calculus course. So eventually, not all of you, but some of you will take a course in complex variables. And all of this stuff will come in very handy for you. Okay, so let's just go through some basic stuff. We started with defining the Argand plane, the complex plane. So let's say I want to plot this point root 5 minus I. Okay, and I'm just going to draw these real quickly for you. So remember, this is the real axis, this is the imaginary axis. There's 0. Now the real part is root 5, so call that root 5. And the imaginary is negative I. And let me do this, because the point's going to be below the x-axis. And call that negative 1. Right? Negative I is negative 1I. So right in here, that's going to be the plot of that complex number z. Right there. You see that? Not drawn to scale. So this is very easy. Plotting them is very simple. It's like plotting x and y. Let's take a look at a different example here. Now, let's say I'm going to go from trig form to, let's go to rectangular form of this complex number. So my trig form, I'm going to say, suppose this is 2 cosine 2 pi over 3 plus I sine 2 pi over 3. Okay, and I want to rewrite it in rectangular form. It's really easy to go to rectangular form. You really just evaluate the trig function. So what is cosine of 2 pi over 3? Remember, that's a 120-degree angle, right? The angle is 2 pi over 3. The reference angle is 60 degrees, and cosine of 60 degrees is negative 1/2 in the second quadrant. So that's 2 times negative 1/2 plus I. Sine is going to be what? Root 3 over 2 in the second quadrant. Again, the reference angle is 60 degrees. And there you have it. You distribute the 2 over, so you get negative 1 plus I root 3. Or let me write it as root 3i, just to conform with the general z is a plus bi form. Usually that's the Cartesian form. So we see how easy that was. And that's what, there you go, that's what that complex number z is. Now let's try one where, suppose this time now I'm going to do something with the exponential form. How's that? Suppose I have 4 times e to the I, and then I'm going to go, I don't know, 7 pi over 4. And we're going to go, this time we're going to go from exponential form to Cartesian. Remember, Cartesian, rectangular are the same thing. Okay, now to do this, actually, we go from exponential form to trig form, and then from trig to Cartesian. So exponential using cis notation, that's going to be cis 7 pi over 4, right? Cis times the argument, not times, but the argument. That's why it's called argument of exponential function, because 7 pi over 4 is argument of the trig functions. So this is going to be what? 4, and the full trig form using cosine as sine. It's going to be cosine 7 pi over 4 plus I sine 7 pi over 4. Again, these we can hopefully evaluate them at this point because we've done them so many times before. Cosine of 7 pi over 4, well, let's see. Here's 1, 2, 3, 4, 5, 6, 7 pi over 4 is right here, right? That means 7 times pi over 4, so I counted 7 multiples of pi over 4. The reference angle is pi over 4. True? Therefore, cosine of 7 pi over 4 and cosine of 45 degrees will be the same. Now, in the fourth quadrant, cosine is positive, so it's going to be root 2 over 2. In the fourth quadrant, sine is negative, times negative root 2 over 2 for reference angle 45 degrees. Distribute the 4 to both fractions, so we get 2 root 2 negative 2 root 2i. And there you have it. Again, the Cartesian form. All right. Let's do maybe a multiplication and a division, and then we're done with this segment. And then maybe I try to solve an equation using a complex number equation. Okay, complex equation. So first, suppose I have two complex numbers. Again, z1 is 2. I'm going to go cis pi over 8. And z2, second complex number, I'm going to go 2 cis pi over 10. Let's multiply and divide these two complex numbers. And we'll keep the values exact. Okay, so because these are not special angles. I'm going to go z1, z2. First, the product. Okay, the product is r1, r2, cis theta 1 plus theta 2. Correct? And well, r1 is 2, r2 is 2. Cis, sum of the two angles, that's pi 8 plus pi 10. There we go. That's 4. Now the LCD here is 40. 40 divided by 8, so that's 5 pi. 40 by 10 is 4, that's 4 pi. So the numerator is going to be 9 pi over 40. Okay, so it's going to be cis 9 pi over 40. And as a complex number, I can write this as 4e to the I, and the argument is 9 pi over 40. There. What if we want to divide them? z1 divided by z2, that's going to be r1 over r2, and then we want to go cis theta 1 minus theta 2. r1 is 2, r2 is 2, and cis theta 1 is pi over 8 minus pi over 10. And this time we subtract. When you subtract, let's see, the LCD is 40, so that's going to be 5 pi minus 4 pi over 40. That's going to be the argument, cis pi over 40. And then we can write in exponential form, right? In exponential form, because r is 1, it's just e to the I theta, which is pi over 40. See, that's how that works. Again, whatever the values, notice I haven't used any calculators in this segment. Good, so pretty light-hearted section again. So you saw the connection between Cartesian form of complex numbers and their counterpart, polar form or trig form they call them. Now let me finish this one just because we got some time here. I mean, 30 minutes, that's not bad. Okay, so in this next example, let's say I want to solve, because you've never done this, I know you haven't, so let me do one for you. Let's say I want to solve this equation. E to a complex number xy equals 7. Now here's interesting. The reason, because I have two unknowns, right? You want to know what's x, you want to know what's y, and we have one equation. Right, so how are we going to solve this equation? Well, let's think a little bit. E to the x plus e to the y, I can write it as e to the x times e to the yi. Right? Now, e to the x is the real. The imaginary part is e to the yi, which I can write using Eulers' formula as cosine y plus I sine y, correct? Equal to 7. Now on the left, let's distribute e to the x, so we get e to the x cosine y plus e to the x sine y I, and then on the right side we just have 7, the real number 7, which I can write as 7 plus 0i, correct? So you kind of see where this is going to go now, right? We have a real part and imaginary part of a complex number. We have a real part and an imaginary part of the complex number on the other side. True? Now, two complex numbers are equal, identical, if the real parts are the same, imaginary parts are the same. So for example, if I have a plus bi equals 7 plus 9i, a is 7, b is 9, correct? So we're going to do a similar work here. So what I'm going to do is, first I'm going to work the imaginary part. Well, imaginary part is going to be equal to 0, right? In other words, e to the x times sine y must be 0, because this is 0 on the other side. Now, e to the x, exponential function, we talked about those extensively in the algebra portion of the course, but just recall what the graph is. Remember, this was the graph of exponential function. The point here is that e to the x is never 0, correct? E to the x cannot equal 0. The function is always positive. Therefore, by zero factor principle, only sine y has to be 0. Isn't that cool? So, because e to the x cannot be 0. And now at this point, we look at the zeros of sine, and that we established way back when. The zeros of sine occur at k pi, where k is an integer. Right? And what do we mean by integers again? -3, -2, -1, 0, 1, 2, and so forth. Right? So that's the set of integers. Therefore, right now we have this. So y is equal to k pi. Now just to write out some numbers again here. So when k is, for example, -3, so -3 pi, -2 pi, -pi, 0 pi, 2 pi, 3 pi, and so forth. These are all solutions to that portion. Okay, this isn't the final solution, by the way. But so far we have the solution for the imaginary part. Now let's focus on the real part. This was the imaginary part. Now let's take a look at real parts. If we equate the real parts, what do we get? E to the x cosine y is equal to 7, correct? Now e to the x cosine y, but then didn't we just solve for y? Y is k pi, correct? Alright, so I can write this as e to the x cosine of k pi is equal to 7. Now, think about cosine k pi. Remember, these are your k pi. If you look at the cosine of these numbers, let's look at k pi. For example, k0, that cosine, remember the unit circle way back when? Cosine is 1. And this is at pi. Cosine is -1. 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi. So it looks like when k is positive, all of these values will cycle through either 1 or -1. For negative k values, on this side, it's the same thing. -pi, -2 pi, -3 pi, -4, -5, and so on. Okay. Therefore, we can generalize that cosine of k pi, therefore, is either going to be equal to 1 or -1, right? Depending on whether k is even or k is odd. So we have established this so far. So in other words, what we're saying is this. On the left side, I can write this equation as e to the x equals 7 or negative e to the x equals 7, right? It's going to be positive for k even, and it's going to be negative e to the x for k odd. Now let's solve these two equations. Well, e to the x equals 7. rewrite this using logarithms. That means x is equal to natural log of 7. Negative e to the x equals 7 means multiply both sides by -1, e to the x equal -7. Well, e to the x, we just showed e to the x is always positive. It can never equal to a negative number. So we can say this is not true, or if you go to log form, you get the same conclusion. So this one cannot be correct. This solution will not exist. So this one has no solution. Therefore, we found one solution for the real part, didn't we? Now x should be natural log of 7. Therefore, when we have x plus yi, remember the original equation was e to the x plus yi equals 7. We can say x plus yi, x is going to be natural log of 7 plus yi, y was k pi, wasn't it? Plus k pi times I. But the catch is this: only when k is even. For even k. Alright, in other words, you gotta go 2 pi, 4 pi, 6 pi, and so on. Well, we can rewrite this. We can rewrite this k pi I as, check this out. I can write this as 2k pi. Instead of calling k even and go k pi, why don't I go 2k pi and let k be integer again? Isn't that cool? You get the exact same outcome. Up here, you're only allowed to choose 2, 4, 6, 8, so on. Well, and they're negatives, of course. And in here, you choose -2, -1, 0, 1, 2, 3. Try these numbers. You'll see that you get exactly the same outcome on both sides. Therefore, there you go. We have the solution. The solution is right in here. Isn't that cool? Now, I know you haven't done anything like this. How do I know? Because you're in a pre-calculus class, and usually in the pre-calculus, the equations you solve are polynomial equations with real coefficients. The solutions may be complex, but you don't solve complex equations. We just solve the complex equation. Okay, folks. Well, we are done with this section. I like to keep it below 40 minutes. Okay, so we just finished talking about complex plane, relationship between the algebraic form of a complex number and the exponential form, and also the trig form. And we got a couple of more sections after this to go. So I'm going to stop here. Thank you for watching, everyone, and hope to have you in another video and another lecture.